David Can here. We're going to be looking at a case of motion where we have an object whose mass is changing. Now, normally when we deal with equations of motion, we have a constant mass, constant acceleration. But in the case of a rocket, the fact of the matter is that most of the mass of the rocket is fuel. When we look at the Saturn V rocket, the total mass of the rocket is about 2.8 times 10 to the 6th kilograms. But the empty mass is about 5% of that. 95% fuel. And as it burns through its fuel then, its mass is changing dramatically. And we're going to try and look at how that affects its motion today. Now with the Saturn V rocket, the thrust is approximately 3.4 times 10 to the 7 newtons, and it runs for about 500 seconds. Now we're making some major approximations here because the Saturn V rocket is actually a 3-stage rocket. These sections here separate as each one runs out of fuel. That helps reduce the mass further. It helps it achieve higher velocities. But we're going to assume that the whole rocket is one stage and that the thrust is constant for a total of 500 seconds. Now the first thing that we might try and do is we might try and look at equations of motion. We're going to assume that this rocket is out in deep space, far from other accelerations due to gravity. That's going to simplify things as well. And so first we might try equations of motion. Now this isn't going to work because the acceleration is not constant, because the mass is changing. We can try and factor that in by trying to take into account the average mass. So the overall mass, or the average mass, is just going to be the total mass and the empty mass over 2. Because at the beginning it's full, and at the end it's empty. And we can try and average these two together, and we get about 1.5 times 10 to the 6th kilograms. Now, this is not going to work because as the mass changes, the acceleration is changing in non-constant ways. But we'll try it anyway. We'll say that we now know the acceleration, which is going to be the force, or the thrust, divided by the mass. That's 3.4 times 10 to the 7th, divided by 1.5 times 10 to the 6th. Now overall, this gives us about 24 meters per second squared. Other things we know that the rocket's going to start from rest, because we're trying to measure top speed, so it's only fair to say that it starts from rest. And we know that it's going to accelerate for 500 seconds, and what we want is final velocity. So we're looking for an equation with A, U, T, and V. This gives us acceleration is change in velocity with time. Now U is 0, so it goes away. And we'll solve this for v by multiplying t to the other side, and we'll get v is equal to acceleration times time. Now the average acceleration we calculated was 24 meters per second, and the time is 500 seconds, and this gives us about 1.2 times 10 to the 4th meters per second, or 12 kilometers per second. Now, that's only going to be a rough estimate, because we talked about how the mass is changing in non-constant ways. We're going to have to analyze the changing mass and changing acceleration over this entire journey to be more accurate than this. So our second method, rather than equations of motion, is going to be calculus. Now for our calculus method, we're going to start by finding the acceleration. Once we have the acceleration, the next thing we're going to do is we're going to integrate acceleration to get velocity. So velocity with respect to time is the integral of acceleration with respect to time. Once we have the velocity, we can then solve for the velocity at the end of the trip, or when time is 500. In other words, we'll solve for v of 500. Well, Well, that's the plan anyway, and it starts with finding a measure of the acceleration. Okay. Well, we already have an expression for the acceleration. We know that F equals ma. Well, we might just try and rearrange this, but the problem is that m changes. So really, we want to say F is equal to m as a function of time times acceleration, which will now also change as a function of time. This is not m times t and a times t. This is m of t, just like f of x. We'll rearrange this to solve for acceleration, and we'll get that acceleration with respect to time is equal to the force, or the thrust, divided by the mass with respect to time. Well, now we need to reason out some sort of equation which is going to describe how the mass changes with time. So we're going to come over on the side here, and we'll create an equation for the mass. Well, we'll start with the initial mass. That's the total mass of the rocket, including all the fuel. As time goes on, we burn up some of this fuel, though, so we're going to take away some mass. We're going to take away a total of the amount of mass of fuel. So that's the total mass take away the empty mass, or the mass of all the metal and stuff in the rocket. So this term here is the total mass, and this term here is the mass of all the fuel. Now, we're not going to take away all of the mass of all the fuel right away. We want to take away some of it with time. So we're going to multiply by t. This way, when t is 0, we're not taking away any mass. We have the full mass left over. But when t is 500, we do want to take away the full mass of fuel. So we'll divide t by 500. That way, 500 divided by 500 is 1, and we take away the full mass of fuel. So this gives us our expression for the mass with respect to time, and we can plug that into our equation for the acceleration with respect to time. F over m naught take m naught me t over 500. So there's our expression for the acceleration. That's step 1. Step 2 is to now integrate this expression with respect to time. That's going to be easier said than done because we have all of these things around t. So one of the things that I'm going to want to do is I'm going to want to try and simplify this expression for acceleration before I attempt to integrate. So I'll say the acceleration is F over m naught take m naught me over 500 t. All I did was move the t under this mass term. And now what I have is something in front of t that I can attempt to cancel out. And here's how I'm going to do it. I'm going to multiply the denominator by 500 over m naught take me. Now that unbalances the equation, so to maintain the balance, I also have to multiply the numerator by the same thing. 500 over m naught take me. So when I distribute these terms in, it has to go into F and each of these two terms. And what I'm going to get is 500 over m naught take me F over 500 over m naught take me m naught, but just take t, because these two terms are going to cancel. It's going to show up everywhere else, though, and that's going to become really ugly. So I'm going to try and create a new term here to simplify things. Because at 500 over m naught take me, this is all constants. 500 seconds, m naught mass, me mass. So I'm going to say 500 over m naught take me t is equal to alpha. And that's just a ratio, without the t. 500 over m naught take me is equal to alpha. That's just a ratio. It's all constants in here. And so I can simplify it as yet another constant. Now m naught is 2.8 times 10 to the 6th, and me is 0.13 times 10 to the 6th. So I can further simplify this as 1.87 times 10 to the negative 4th is equal to alpha. So not only do I have my constant, I know what it is as well, and I can make that simplification. And I'll say that acceleration is alpha f over alpha m naught take t. And all of a sudden this is starting to look more simple. Because remember, alpha is just a number here. Now what I'm going to do is I'm going to create an expression for the velocity with respect to time by integrating the acceleration with respect to time. So this is the integral of alpha f over alpha m naught take t dt. Now this is going to work out to a logarithm because I'm integrating 1 over t. But the trouble is I have negative t in my denominator, so the derivative of negative t is negative 1. So I'm going to rearrange this a little bit and call this negative 1 times negative alpha f. That should be fair. Multiplying by negative 1 twice does nothing. Over alpha m naught take t dt. Now when I integrate this, I have a negative 1 on top to cancel with the derivative of negative t. I can also pull out negative alpha f, because those are just numbers. That's a constant. So I get negative alpha f out front over negative 1 times the integral of negative 1 alpha m naught take t dt. Now I need to perform this integration. So the integral of 1 over a function of f, that gives us the natural log of that function. Alpha m naught take t. And then finally we have our constant of integration c, and that's our velocity. Okay. Well, now that we have the velocity, let's see if we can find that constant of integration. Because we know that when time is 0, the velocity is also 0. So v of 0 is 0. So v of 0, that's 0, and that's negative alpha f times the natural log of alpha m naught. Now t is 0 plus c. Or in other words, c is equal to alpha f times the natural log of alpha m naught. And so overall, the velocity is negative alpha f times the natural log of alpha m naught take t plus alpha f times the natural log of alpha m naught. Okay, that looks kind of ugly, but we can take advantage of some factorization. Both terms have alpha f in them, and both terms have natural logs. In fact, they have natural logs as a subtraction. So we can first simplify this as alpha f times the natural log of alpha m naught, so that's this term over here, take away the natural log of alpha m naught take t. My alphas keep looking like 2's. Okay. Now that we have a subtraction of logs, we can take advantage of log laws as well. And we can say that velocity with respect to time then is alpha f times the natural log of alpha m naught over alpha m naught take t. Okay. Finally, we have one expression which doesn't look too bad, something that we might choose to work with. So at this point, we're going to try and solve for that function when time is 500. So we're going to solve for v of 500. Now, alpha we already found was 1.87 times 10 to the negative 4. Now, the thrust from what was given was 3.4 times 10 to the 7 newtons times the natural log of alpha is still 1.87 times 10 to the negative 4. M naught is the total mass of the rocket. That's 2.8 times 10 to the 6th meters per kilograms. And we'll divide that again by alpha M naught, 1.87 times 10 to the negative 4 times 2.8 times 10 to the 6th, and then take away T. That's 500. Right, at this point we have one expression with just numbers in it. There's no more variables, nothing's left. So all we have to do is get out our calculator and solve for this. And when we do, what we find is 1.9 times 10 to the 4th meters per second, or 19 kilometers per second. Well, that's a bit different than before. And like we said, this comes from some of the assumptions that we made when we did our first, more simple calculation with equations of motion. When we did this calculation with equations of motion, we assumed that acceleration was changing in a constant way. But when we look at our equation for acceleration, this is a rational function. It's not going to change in a constant way. And what we find is that using calculus, the more exact answer is just a little bit different. And we find a more precise value here. Now, interestingly, I looked it up, and it turns out that the actual max velocity of the Saturn V rocket is about 40 kilometers per second. So we were off by a fair amount here. But we can probably attribute it to not taking into account the different stages and the different thrusts from the different stages, as well as the loss of additional mass when the rocket sheds its extra stages. Hopefully that'll account for that difference. But anyway, I hope you enjoyed this demonstration, and hopefully I'll get a few more out for you soon. Thank you very much.